Hey, Geometry. So today we're going to get into section 8.3, special right triangles. And so last section we looked at Pythagorean theorem and we looked at some Pythagorean triples that the triples are the ones that are nice whole numbers, which is fine. Those actually come up a decent amount on math tests and things like that, but they don't come up that much in reality relative to how much they show up on math problems and tests. This stuff does, though. These 45, 45, 90 triangles and the 30, 60, 90, they're just nice even divisions that we will see a lot. So properties of these, we'll start out with our 45, 45, 90 degree triangle. This is a very common one where it's a right triangle. We like right angles. If you look around, you'll see right angles all over the place. That perpendicular lines. And so you'll see a lot of those. And then if you split that perfectly in half, you get a 45 degree angle, right? And so if you cut straight across a 90 degree angle, you'll get that. And so that's a very common angle. It's half of 90 degrees. And so if we're dealing with a right triangle where we do something like that, and really another thing you think about this is a square cut in half. So if we see this in a triangle, we know that we're dealing with an isosceles right triangle where both of those angles are 45, since this all has to add up to 180. These two add up to 90. That one's 90, adds up to 180. So you'll have two sides the same. And so if that's the case, you'll have this relationship. But you're going to have x, and then root 2x. So two sides the same, root 2. And you could figure this out with the Pythagorean theorem. You don't need this. You don't need me to tell you this. You could have set up x squared. If we called this like a... b, what is c? So we would set up x squared plus x squared is equal to c squared. And you could go ahead and solve it, and you get x squared plus x squared. Oh, that's 2x squared. And then that's, equals c squared. And we take the square root, and we get the square root of both sides. And so we get c is equal to the square root of 2 times x squared. Well, it turns out we can split that out. X is a perfect square, so we can write that as like the square root of x squared times the square root of 2, and that's just x root 2. So c is equal to x root 2. And so we could solve that. You don't have to memorize that. You could reprove that if you wanted to. Just know that those two sides are the same. And then so there's this kind of pattern that you can remember. If you have two sides the same, and then the third side is root 2. So two sides the same, root 2. So two sides the same. And then root 2. That's just kind of a way of remembering that. These show up a lot. Let's go through a few of them. So if this is 8, we know this other side would also be 8, and so this side is going to be 8 root 2. It's as easy as that. So we can make it a little more clear. Like that, it won't always be that easy, but if this is x, in this case I'm basically saying x equals 8. Well, that's a bad example. If this is because that's x over there. So if this is my a, or something like that, and then this would be 8, that number times root 2. And so that's what that side's going to be. You could also set up and solve. You could set up 8 squared plus 8 squared, and equals x squared, and solve and spend some time with it. But you want to be fast on these. You don't want to have to do that. So you can remember that this side, that side's the same, and then that side's going to be times root 2. If we do this, we'll get 64 plus 64, which is kind of a waste of time to put it like that, square root of 128, because what we're going to do right here in a second is when we take the square root of that, we can turn that into 64, square root of 64 times 2, and that turns right back into 8 root 2. So x is 8 root 2. Over here, this time they give us the hypotenuse side, and notice that there's a root 2 in that. So that's like, if this is x, this is our x root 2 side. So I could say x root 2, let me bring that out there a little bit, x root 2 is equal to that. If this is x, that's x root 2. And so we can then just kind of solve for x, divide both sides by root 2, you get 3. So we effectively divide that root 2 away and get 3, and if we wanted to, that's 3. And so x is 3 in that case. This side, if this is a 45, 45, 90, if that's 4, this is 4, this is going to be 4 root 2. And we can quickly get through what that's going to be. You could also show that another way. this time, my hypotenuse is 18. So if this is x, then this is my x root 2 side. So I'm actually set up an equation here, x root 2. And so to get these other sides, I'm actually going to divide by the square root of 2. So if I set up this formula, x root 2 is equal to 18. If I divide by root 2, we get x is equal to 18 over square root of 2. All right, well, this creates a problem. This is something that we need to make sure that we're comfortable with, is we don't like having radicals in the denominator. We consider that not to be simple. Of course, we could just type in and get the decimal 18 divided by the square root of 2, and maybe that would be acceptable, right? 12.72. That's actually what these lengths are going to be. So these are 12.73, I guess, if I'm around. But what if you want the exact answer? It might show up in the multiple choice. You don't want the rounded decimal. So the way we rationalize the denominator is we multiply the top of the fraction and the bottom of the fraction by the same thing. So we know that doesn't actually change the value. So we're going to actually multiply the top and bottom by square root of 2 and square root of 2. And so this ends up being 18 root 2 over square root of 2 times square root of 2 is square root of 2 squared. I'll write that temporarily, although we'll quickly realize that that just cancels out the square root. That's why we do this, is actually to cancel out their square root. And so we just get divide by 2 on the bottom. And then now we can actually reduce this fraction, 18 over 2. We can reduce that fraction. That reduces just to 9 root 2. So this side over here would be 9 root 2. So 12.73, and to verify, 9 square root of 2 is 12.73 as well. All right, same thing here. This is just going to be, we can maybe skip a little bit of the work, 16 over root 2. Well, now we need to clean that up. We'll multiply by root 2 on the top, root 2 on the bottom, and so that ends up being 16 root 2 over, and then root 2 times root 2 is 2, and that just becomes 8 root 2. So that's what x would be. And notice that if we multiply 8 root 2 back times the square root of 2, we end up with square root of 2 times square root of 2. It's 2 times 8, which is 16. So it should work out in both directions. And the last one, divide by root 2. That one sets up nicely. It's 24, what x would be. All right, so determine the length of the leg of a 45, 45, 90 degree triangle with a hypotenuse length of 25 inches. So just kind of describing the same thing in words, we could draw a picture of it. And this is a 45, 45, 90, and the hypotenuse length is 25, and so they want us to know, determine the length of the leg, and so really there's 2 legs, but they're both the same, and so we just need to divide by root 2, and so this ends up being 25 over root 2, which is, we want to rationalize, and so that's going to be 25 root 2 over square root of 2 times square root of 2, which is just square root of 2 squared, so we just end up with 2 in the denominator, and this is 25 root 2 over 2. And technically, that is simplified. I know it doesn't look super simple, but technically that is. We can't reduce that 25 over 2 fraction. We definitely can't cancel this. Like, these radicals can divide, but you can't mix up the non-radical numbers with those. And so 25 over 2, yeah, we could get a decimal value for this, and honestly, that's a lot of times just the nicest, but you need to be able to identify it both ways. So 25 root 2 over 2 is also 17.68. Right, so 17.68. That would be the length of the 2 sides with that 25 for our hypotenuse. All right, so that's one of our very common special right triangles, and we'll look at the other one in just a second in the next video.